Okay, and then we will go to the next section. That is section 2.3, energy transfer efficiency. Okay, before talking about this, first we need to talk about the definition of efficiency first. Okay, well, in daily life, if we describe a process to be efficient, it means that you only need to give the least amount of input to have a certain amount of output. Well, for example, if a certain work can be divided to several people instead of one person, the work can be done in a shorter amount of time theoretically. Okay, of course I say theoretically because I don't know if your team works well. But assuming every people have the ability to do the work can be done in a shorter period of time. Okay. Similar definition applies to that in thermodynamics, where we use efficiency to indicate the performance of a device. Okay? Well, it's defined as the desired output divided by the required input. That's this one. Okay? That's this one. The desired output is different for different devices, so it is important to clarify how efficiency is defined for each process. Okay? Here we will give some examples. Okay? For example, consider the combustion of a fuel. Okay? After a fuel is put in a combustion chamber, okay, it's combusted, and the energy is released for different uses. Okay? Well, if it is carried out in your engine, then the energy will be used to propel the car. Okay? Before talking about the combustion efficiency, we need to first define the energy input. Okay? It should be the heating value of a fuel. Okay? It's defined as the amount of heat released when a unit amount of fuel originally at room temperature. Okay? Remember, originally is at room temperature, is combusted completely, and the products are cooled to room temperature. Okay? The efficiency of combustion can be defined by this expression. That's the efficiency of combustion equal to Q divided by the heating value. Okay? Q will be the amount of heat released during the combustion. Okay? So originally, after you burn the fuel, you will have all of the energy here. That's the input. Okay? That's the input. And the desired output, we need to extract the heat released during the combustion for different uses. So this is the desired output. Okay? As most fuels contain hydrogen, when hydrogen burns, water will be formed. Okay? We will use two quantities to indicate whether the water inside the combustion products will be in liquid or vapor form, which depends on the pressure during the combustion. Okay? The lower heating value, we will say that these are LHV. Okay? LHV is the heating value when the water produced is in a vapor form, while the higher heating value, that's the HHV, indicates the heating value when the water is in a liquid form. Okay? So it's different. Why? Well, you can see that the difference between these two would be the latent heat of the vaporization of water at the room temperature. Okay? Both LHV and the HHV can be used to indicate the heating value, depending on the situations, but it should be made clear whether the heating value is based on the LHV or the HHV. Okay? Well, when it leaves in a vapor form, that means some of the heat is trapped inside the water as a latent energy. It is not released. Okay? So it will be the lower one. For the higher one, because the water will be in liquid form, the latent energy has been released as a latent heat of vaporization. So you will get a higher heating value.